All right. So we've got the electron dot formulas, that's the black part of this. And we've got the sharing arrangement, that's the circling part of this. From that we do the Lewis dot formula. So I've got a pair of electrons that are lone pairs on the phosphorus, and I have a shared pair here and a shared pair here and a shared pair here. So I'm going to put those here and here and here. You squeeze the electrons in between the element symbols. And that's the Lewis dot formula. You have to identify the number of sets of electrons there are around the atom to which everything else is bonded. I sometimes call that the atom in the middle. Okay? And shared or sets of electrons fall into two categories. One category is lone pairs. Well, this is a lone pair right here. So that's one set right there. Okay? The other category are all the groups of electrons shared between two atoms. So I have three of those sets. I've got a set here, and a set here, and a set here. Okay? Yes?
I got a question. When you find out how many electrons something got, just think about if we were doing medium. Will we just count over like we regularly do 1, 2, 3, 4, 5, 6, and just pick down 5 for that?
What's the element again?
Niobium? Nibium?
Niobium?
Niobium? Yeah.
Well, niobium is a metal, so it doesn't do this this hybridization. It doesn't do sharing of electrons.
So does it?
No. Only the nonmetals do this. That's over here. So the stair step right here divides metals on this side from nonmetals over here, and only these nonmetals do this covalent bonding.
Okay. So
Okay.
it doesn't matter how far you are down the thing, whatever you just count over, and that's how many electrons it has? Did you say that?
Well, if I have, you count over in the sense that you're identifying the fact that you have 1, 2 s electrons and 1, 2, 3 p electrons in the valence level of phosphorus, because phosphorus is right here.
Yes, sir.
That comes from the orbital notation. Okay, we figured out the orbital notation so that we found out there were 2s and 3p electrons. Okay, so with orbital notation, the arrows represent electrons. We don't do anything with the lower level. We only do things when we're talking about electron dots. We're only talking about the valence level, and the valence level is the only place that bonding takes place. Okay, in college you may find out other things, but right now we're just going to assume that only the valence level, the s and p orbitals in the highest energy level, will do any kind of bonding. Okay.
Yes, sir. So you could do one with iodine then.
Yeah, you could.
Can you do one with iodine after that?
I could, but I have I'm covering. I was asked to do all of this, and that would be 3 different kinds of hybridization here. So I've got a while before I get there. Okay, but sure, iodine will work the same thing as chlorine. We went 1, 2, 3, 4, 5, 6, 7. Iodine is 1, 2, 3, 4, 5, 6, 7 electrons.
Okay, never mind. I got it now. I got what I need.
Okay, all right. Okay. So we've identified 4 sets of electrons then. So what kind of geometry do I need for the electron pair shape if I have 4 sets of electrons? A tetrahedral. Okay? And that looks like this. You got the element in the middle of everything. That's the phosphorus. Everything's bonded to the phosphorus. And I got 4 sets of electrons, so I got one coming up here, and one coming out this way, and one coming down here like this, and one going right behind the paper, and then we picture that as a dotted line. And so all these are single pairs, 2 electrons on each of these locations. So we want those sets of electrons on here as well. 2 electrons on each of these. So one of these sets is that lone pair. The other 3 sets are these shared pairs. Okay, this is what's shared between chlorine and phosphorus. Okay, so this is a tetrahedral. That's the geometry. And this is an electron pair shape. And the electron pair shape is the drawing that has an atom in the middle and has only electrons on the end of the arms. Okay, that's an electron pair shape. The next step in this process is to redraw exactly the same drawing. Students that mess up getting the molecular shapes right mess up in these next 2 steps because they don't follow the process. Okay, if you'll follow the process carefully and have been following the process all along, you probably will get the shape right. Okay, so we're going to redraw exactly the same shape. Okay, what I need to do now is identify what sets are shared with atoms. Okay, so this set right here is shared with the chlorine. This set right here is shared with the chlorine. This set right here is shared with the chlorine. So there are 3 sets on this that are shared with chlorines. It doesn't matter which of these arms you put the chlorines on. Okay, the 3 types of shapes we're starting with electron pair shapes. It won't matter for those shapes where you put the outlying atoms, the attached atoms. It will matter in some more complex type molecules you'll get to in college, but not the ones that we deal with in here. Okay, so you can put those chlorines on any one of these 3 of these 4 arms. Okay, doesn't matter. I'm going to choose to put it down here. So that we got a chlorine here. And a chlorine back here. And a chlorine out in front here. Okay? And then we still have this pair of electrons here. All right? The geometry is still tetrahedral. We didn't change the shape of it. But we can't call it an electron pair shape because an electron pair shape only has electrons on the arms. This has a mixture of electrons and element symbols or atom symbols. It would be a molecular shape if all the electron pairs were gone, but they aren't gone yet. So it can't be a molecular shape yet. It can't be an electron pair shape. Well, we're going to call this a modified electron pair shape. Well, yeah, that's the next stage. But you have to draw the same drawing again. Okay? Now, a lot of students, they start, getting this seems like a lot of stuff to do and seems tedious, and they start taking shortcuts, and they end up with the wrong drawing at the end. They lose a lot of points. So don't take shortcuts, okay? All right, as I showed you when we went over this, I give points for each of these things. All right, this is a way of getting the correct shape every time, at least with the simple molecules we deal with, and it's a place to build some skills so that you have a foundation for what you need to do after this class. If you go to college, you have something to build on. Okay, and so we want to redraw exactly the same drawing. We redrew exactly the same thing to do this one. Now we're going to redraw this one to get to this one, to get this last step here. So yes, you're correct, but don't get ahead because you got to do the steps, okay? All right, and so the last thing is we're going to erase that lone pair up here. the shape we end up with is this. And so, since we no longer have any lone pairs, this is the molecular shape. So this isn't called tetrahedral anymore because a tetrahedral has 4 arms. This one has 3. And there are 2 different types of drawings that have 3 arms. This one's a trigonal pyramidal. The other one is a trigonal planar. Okay, but this one's kind of, it's not flat. It's kind of puckered up in the middle. Okay, so this is a trigonal pyramidal. And this is a molecular shape because we don't have any lone pairs left. All right, so that's a step-by-step process for finding the molecular shape of this molecule. And that was a question, wasn't it?
Yeah.
For finding molecular shapes? All right, do we want to do some other molecular shapes, or are we okay with just you looking at the steps? Who asked this a while ago? Who was that? You? Do you want to do some other molecular shapes, or are you good with this? Okay, yes.
Are we gonna have to do any of the drawings with like all the bonds? Like
Yeah.
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 Okay. Can we do
Well,
that?
let me back up here.
Do that?
I'm not telling you what's on the test. Have we covered it in this unit? If we've covered it in this unit, in fact, if we've covered it in this unit or any previous units, it could be on the test.
Okay. Well, can
Okay.
we go over a problem with getting to like that one?
Yeah, we can do the shape of the bonds on this.
Okay.
Okay. If we're drawing the shape of the bonds, then these are all sigma bonds. Okay, but what we're really drawing is the bonds and the lone pairs. So it's more like what this one is right here. Okay, so we have a phosphorus in the middle, and sigma bonds are those long balloon shapes like this. Okay, and you put a chlorine on the end here. And since this chlorine is coming out away from the board, it's like this pen is, I write this pen flat on the paper, but we're going to tilt it up toward you like that. In fact, I'll put it in the camera a little better. You can see how the pen, see how it gets fatter up here on this end right here when I turn it toward the camera? That's what we're going to be doing here. So this is going to come out toward you like that. Okay? And I put the chlorine out here. And then this one is back behind the paper, so that's like I had it tilted back like this, where it's bigger up here and smaller down there. And with the molecular shape, you've also got to show the shape of the lone pairs. And the lone pairs are going to remain in that single balloon shape we did. Okay? So this is a lone pair. And that means I have 2 electrons in here. We need to identify the hybridization here. Okay? If you have only single bonds, and 2 shared electrons between 2 atoms makes a single bond. 2 shared electrons between 2 atoms makes a single bond. A pair of electrons that aren't shared with anything, that's called a lone pair, or an unshared pair. If all I have are single bonds and lone pairs, then that hybridization has to be sp3. Okay? So I can label this sp3. All single bonds and all lone pairs have to come from hybrid orbitals. All single bonds and all lone pairs have to come from hybrid orbitals. So if I'm hybridizing 4 things to get 4 single bonds plus lone pairs, 1, 2, 3, 4, then I have to hybridize 1s, and 3 P's. So 1s and 3 P's makes 4, right? Okay. So this is going to be sp3. This is going to be sp3. All these are sp3s then. But now these are sigma bonds. That's that O with a swish or dash on the end of it there. And all these have 2 electrons in them. That makes sense? Everybody good with that? Yep.
So what would it be called if they were sharing 4 electrons?
Okay. Well, let's go through this process for a molecule that has phosphorus and iodine. Okay, and I can make a molecule from that that has that double bond in it. Okay. So we'll put phosphorus. Let me see here, just to write it in the right order. We'll do phosphorus and sulfur and iodine. Okay, phosphorus and sulfur and iodine. Okay. All right, we said we have phosphorus has 5 valence electrons. How many valence electrons does sulfur have? Kayla, how many valence electrons does sulfur have?
6.
6, good. One, 2, 3, 4, 5, and 6. Okay. And how many valence electrons, Bo, does iodine have? How many?
7.
7, good. One, 2, 3, 4, 5, 6, and 7. Now sometimes you have to try something and see if it works. If it doesn't work, you try something else. Okay? So you might try putting these together and it's like, this isn't working. Well then, do it again. Just leave that drawing on the paper so you don't do the same thing a second time and try it a different way. Okay? In order for this to actually work, I know, because I've been doing this a while, that I've got a bond between phosphorus and sulfur twice. And that's that double bond you were asking about, okay? And then I bond one time with this iodine over here. Okay? Well, now the phosphorus is in the middle still. Okay? The Lewis dot formula then is going to be here. And it doesn't matter whether the sulfur's on the right, left, top, bottom. You got to, doesn't matter where you put them as long as they're on one of the 4 sides. I'm going to put iodine over here. And there's just 2 electrons shared between the phosphorus and the iodine. So I'm going to put 2 electrons here. But there are 4 electrons shared between the phosphorus and the sulfur. I could put the sulfur up on top, I could put it on the right side, I could put it down below. Doesn't matter. But you have to show 4 electrons between the phosphorus and the sulfur. Okay? Like 4 corners on a box, like that. Okay? And now we have to account for the lone pairs. The iodine has 1, 2, 3 sets of unshared electrons, or lone pairs. 1, 2, 3. Phosphorus has 1 lone pair up here. And sulfur has 2 lone pairs. 1, 2. Okay? And that's the Lewis dot formula. Okay? Do you want to do molecular shape and the balloon model stuff, or what?
The balloon model.
The balloon model, okay. So for the balloon model then, that's the double bond between the phosphorus and the sulfur. I'll put the phosphorus here and the sulfur over here, and I'll put the iodine back here. Okay. So for a double bond, let me show you this. Well, I had this earlier. Okay. For a double bond, you've got to have a hybrid orbital for the sigma part of that bond, and a p orbital that's not hybridized. Okay, so I have to have some kind of hybridized orbital for a sigma bond, because a double bond has to have both a sigma and a pi bond, and the pi bond comes from a p orbital. Okay, so I'll pencil that in. Okay, so here's a hybrid orbital on the phosphorus, and here's a hybrid orbital on the sulfur. Okay, and both the phosphorus and sulfur also have to have a p orbital, unhybridized p orbital, and that's a double balloon shape. That's what we learned to do in the last unit. There's a p orbital, and that's a p orbital. Okay, got that? So if we go back up here and look at this Lewis dot formula, I've got a double bond right here. If I have a double bond on an atom, and that's all, and I don't have a second double bond, just one double bond, the hybridization of that atom has to be sp2. Okay? If I have nothing but single bonds and lone pairs like I had here, that's sp3. If I have a triple bond on an atom, that has to be sp hybridization. Also, if you had two double bonds on the same atom, like carbon dioxide, that's sp. Okay? All right, so we've got a p orbital that's not hybridized. I'll go ahead and label this as p. Y'all want it to be px, py, or pz?
Yeah.
Px, she says, okay? We'll call this px then. All right. So if I have a hybridized orbital on both these two atoms and a p orbital that's unhybridized on both these two atoms, the hybridized orbitals can form a sigma bond like this. Okay. And I'll kind of erase the bond markings in here to make it easier to see what I'm doing with the labeling. Okay. So that's a sigma bond. And there are two electrons in a sigma bond. And we said the hybridization is going to be sp2. Okay, it has to be sp2 if I have a double bond on it. Okay. For the p orbitals, then, they're horizontal, or they're parallel to each other going this way, and the pi bond is going to be parallel going this way. Okay, this p orbital here becomes a pi bond like this. I'm going to erase the pencil marks now, so you can kind of see the result of the getting you that pi bond. Okay, so that's the pi bond, and if it's px, then it's the pi bond is pi x. Now there are two electrons in here. That gives you all four electrons, two in the sigma bond, two in the pi bond. You can put the two electrons down here, you can put two electrons up here, you can put one here and one here. It doesn't really matter as long as you have those two electrons in that pi bond. For this one, I'm just going to put one here and one here. Okay? All right, then the sulfur has two lone pairs here, and lone pairs are going to be, they're going to look like this, like those hybridized orbitals. Lone pairs have to come from hybridized orbitals. Okay, so hybridized orbital is a single balloon shape, and I got to have two of those. Oh, I got a pink marker here somewhere. Oh, there it is. Let's do that. So the hybridized orbital came from the lone pairs stemmed from a hybridized orbital. This has a double bond on it. It must be sp2. So the hybridized orbital are sp2 hybrids, okay? So this is sp2. And the other lone pair is sp2. So once an atom is hybridized, all the sigma bonds in lone pairs have that hybridization. These have 2 electrons in them, and they're lone pairs. Yes, sir.
I have a question.
Well, I'm not really finished with this. Can I finish this first?
Yes, sir, you can.
Okay. All right. So between the phosphorus and the iodine, there's a sigma bond. Okay. Well, a sigma bond is this long balloon shape or hot dog wiener shape. Okay. So I'll put that over here like this. That's a sigma. There's 2 electrons in here. Let's see, if the phosphorus is sp2, then the sigma bonds in lone pairs have to be sp2. Then the iodine has 3 lone pairs on it. So I'm going to have a lone pair coming like this, and a lone pair really kind of coming out toward you, and one kind of tucked in behind everything. Let's put that in blue, I suppose. All right, so this is a lone pair. Actually, this is going to be sp3. If an atom has nothing but lone pairs and single bonds, that hybridization is sp3. And a lone pair is going to have 2 electrons in it. And I didn't put 2 electrons yet in this one. I haven't even bothered to label the bottom one yet. Okay. If we were to do the shape of this, you didn't ask me for that, this would be, I got 3 sets of electrons here. What's the shape you get for the electron pair shape when you have 3 sets? Trigonal what? Planar. So the trigonal planar is like this, and this, and this. It's a trigonal planar electron pair shape. Then we redraw the same thing, and I have to put 4 electrons on one of these arms here. Redraw the same thing again, and I'm just going to skip over the redrawing first because you didn't ask me for this. I got one lone pair on the phosphorus, one shared pair with an iodine, and I've got a double bond going out here to the sulfur, and so I'll put the sulfur out here where I have the double bond, the double pairs are located, okay? And so that's a trigonal planar modified electron pair shape, and you'll end up with a molecular shape. And so I'm skipping steps, but don't do that on a test. Make sure you do all those little steps where you redraw things, okay? I'm just showing you that's how you get there. So you get a bent molecular shape. Okay? And I actually left, I just realized that when I did that. It's always good to do those things because you can see what you leave off. There's a lone pair of electrons on this sulfur that are back kind of behind this. Right in here, I didn't put that in there. Okay? So really I should have had this bending down a little bit this way. That's a lone pair. But you were only asking about the double bond. That's all I was thinking about, I suppose. But, I mean, that's no excuse. I should know that. Okay? Everybody got that? So this one doesn't come out to be tetrahedral. This one has to be trigonal planar, which then when you go through the process and eliminate the lone pairs, you end up with a bent molecular shape. Okay, Bo, you said you had a question.
Yes, sir. How did you tell if they on the x-axis and the y-axis?
We learned about that when we were in the last unit, and at this point when we're doing these pi bonds, you don't have to figure out which one it's on, you just choose it to be on one of those.
Yes, sir.
Okay? So we just chose to be X. We could have chosen Y or Z. If we have two pi bonds, they have to be on different axes. That's the thing I want you to remember, is that you can't have two pi bonds both on X or both on Y. You have to have one pi bond on X and one on Y or something like that. Okay? Where X, Y, and Z are is not so important as the fact that you know there are X, Y, and Z axes. Okay? We're talking about something that's happening in space. If I have a spaceship, all right, and it's flying, you know, between the Earth and the Moon, for example, which way is up in space?
You can't tell, really, can you?
You can't really. That's like this right here. You can't really. So up is wherever your head is, basically. All right. So when you're in space, you consider that axis to be the y-axis, I suppose. Okay, you could think about it like that. All right, and your right arm and left arm is the x-axis, and what's out in front and behind you is the z-axis. I think it's actually different than that, but that's okay. For us, we can think about it that way.
Yes, sir.
So this is happening in space. So in this case, you can kind of choose which one you want it to be. All right, what else you guys want to go over? It's everybody's responsibility to have questions. If you don't have questions, I start Unit 4. Just saying.
You can start Unit 4 right now.
I do have to stop Unit 4. I'm not going to take half an hour and do nothing.
We could do.
All right. So Unit 4 is about nomenclature. So let's take notes on this, please. Unit 4 is on nomenclature. Nomenclature is a naming system. Somebody pointed out in first period, and I had never really even thought about this before. All the halogens have an INE ending. I never really thought about that before. And so when you have an element name with an IDE ending, INE ending, that tells you right there that's a halogen. Except for helium, all the noble gases have an ON ending. So if you have an element name with ON on the end, I don't see any others, that's probably a noble gas. All right. All the metals over here, except for the ones that we've really known about for hundreds of years. So we've known about iron for hundreds of years, and cobalt and nickel, copper and zinc, but we haven't known about these others. Most of these have an IUM ending. Well, those polyatomic ions we dealt with yesterday, we also gave those IUM endings. So the fact that they're metals also means that they tend to lose electrons, and when they lose electrons, they become positive ions. Well, that's just like those positive ions we dealt with yesterday, those polyatomic ions, those more than one atom ions, that if they're positive, they have an IUM ending on the name. Okay, so that's a naming system. I didn't even realize that until somebody asked me about that in first period today. First time in all these years somebody's asked me about that. Notice that. Well, there's a lot of naming conventions and systems in chemistry. Okay, and for chemistry, when we're naming compounds, and that's what this nomenclature is about, naming compounds. And there are a few other things we'll deal with in that unit too, but primarily it's all about naming compounds. We have 4 categories of compounds that we have to name. So in this unit, we've been dealing with covalent compounds, but there's 2 categories of covalent compounds. There's a non-organic covalent, and there's an organic category, which most of the time is also covalent. That's 2 of the categories. Then we got a category that's called ionic. And we have to be able to name the ionic compounds first, because the acid names, the non-organic acids anyway, we have to first name them like ionic compounds and then change the name to acid names. Okay? There are a category of acids called organic acids, but we won't be dealing with those in here. Okay? We'll deal with some really simple organic compounds. We won't deal with the more complex things like organic acids and organic bases and things like that. Okay? All right. So we'll begin then with this non-organic covalent group. Okay? And so you got to go back to kindergarten and learn to count all over again. Okay? Because there's a set of prefixes you need to know for covalent compounds. So the prefix mono means 1, and we almost never use that in naming. Very rarely are compounds named mono something, like carbon monoxide is one case where we do use that mono prefix. So we kind of skip over mono because we don't use it very much. Okay? But the prefix for 2 is di. That's the one we use. There's actually more than one prefix for 2. You could use bi, but we only use di for this stuff, okay? So, for example, what do we normally call this? Water. Okay? But if we were naming it according to this systematic system, that would be dihydrogen.
And that's the non-organic?
Yes. Dihydrogen oxide. There's a di right there, okay? All right. And then if we have 3, that's tri. like a tricycle. Four is tetra. Five is penta, like pentagon. Pentagon is a building that has 5 sides. 6 is hexa. 7 is hepta. We talked about the valence level needing a certain number of electrons. How many was that? 8. And what do we call that when it has 8? Octet. Well, that's the prefix here. Octa. You know, an octopus has 8 tentacles. Okay. 9 is nona. And what do you call 10 years? A decade, or this in this case is deca. Yeah.
What is 9 again? How you pronounce 9?
Nona. So you're just going to have to memorize these. Okay? Now, organic compounds are based on carbon. Carbon's the backbone of organic compound. So, methane we've dealt with already. Okay? And in methane, the hydrogens are all bonded to the carbon, and so carbon forms that backbone. Okay? There's also C2H6, which we could also write in the form CH3CH3. And that has 2 carbons in it. And that's called ethane. And that looks kind of like this. And again, everything's bonded to the carbon, so that forms the backbone of the structure. And so the prefixes are a little different for our organic compounds, and they're used in a different way. In the non-organic covalent, the prefixes tell you how many of any kind of non-metal atom you have. Okay? The prefixes, or actually these are the root names. The root names for organic tell you how many carbons there are in a chain. Okay? Does that make sense? The prefixes in non-organic covalent tell you how many of any number, any type of nonmetal there are in the compound. The prefixes in non-organic covalent tell you how many of any of the nonmetals you have. The root names in organic covalent, or just organic, those root names tell you how many carbons there are that are bonded together. So in organic, the root name tells you how many carbons there are bonded together. Now, one of the things I've been encouraging you guys to do is learn how to do effective notes, because, you know, in college, most of the time, the professors don't tell you, take notes on this like they do in high school a lot of times. If you hear me repeat something, or if I sound like what I'm saying it's really sound like important, you probably should write it down. Okay? So I'm trying to encourage you to think about that. And a lot of you are. You're getting better at this. Great. Okay? I want you to do well with this kind of stuff in here, so that you are, have the skills to do that when you get to college. All right? You think about it.
I'm also writing the first one about the prefixes.
Huh?
Can you repeat it one more time?
in non-organic covalent, the prefixes apply to any non-metal in the compound. The root names in organic covalent, or just organic, the root names in organic only apply to the number of carbons. There are other prefixes for the number of other atoms, but we don't even get into that in here. Right now we're just dealing with those root names. Okay? All right, so we said that.
Do these names deal with organic and ionic and acids also?
No.
They don't?
No, these only work for non-organic covalent. The ones I will give you here only work for organic. Okay? So there is a root name for one, and that's meth. And the root name for two is eth. So we had methane and ethane, 1 carbon and 2 carbons. Okay? And the root name for 3 is prop. And the root name for 4 is bute. Please try to remember not to mispronounce that. It's bute.
Can you write it down? Yeah, I can't see.
The root name for 5 is kind of like this 5, only without the A on the end. It's pent. The root name for 6 is like this one. It's hex. For 7, it's kind of like this without the A on the end. Hept. 8 is oct. 9 is non. And 10 is dec.
So you want us to memorize all these?
Yep. Kind of got to memorize all of them. Okay? Uh-oh. Hold on a minute. My chair's about to come off the platform for some unknown reason. I don't know why. All right. With ionic, we're going to have a numbering system for the metals in ionic compounds. And those are going to be Roman numerals. We'll talk about how you apply those later on. But how many of you don't know the Roman numerals up to 10? You don't know them? Okay. So let's go through that. Then a Roman numeral 1. Well, I probably should have written 1 and then say that's what that is. So let me change that around to like this. So this is the number 1. It will be in a minute. Hang on a second. So that's the capital letter I. And 2 is the 2 I's. And 3 is 3 I's. We could make it 3 separate I's, I suppose. Okay. So how do you know which Super Bowl it is if you don't know Roman numerals? Well, those letters they put on the screen, those are Roman numerals. Oh, you don't know what they are? Okay. All right. And so 4 is IV. And 5 is V. And 6 is VI. 7 is VII. 8 is VIII. 9 is IX. And 10 is X. So I guess you're going to have to memorize those too. But I'll give you a little hint. A lot of these numbers are at the top of the periodic table. Okay? So right here over hydrogen, if you look there with me, that's 1A. And that's 2A. This is 3B, 4B, 5B, 6B, 7B, 8B, 1B, and 2B. To be or not to be. 3A, 5A, 3A, 4A, 5A, 6A, 7A, 8A. So, except for 9 and 10, those numbers are kind of at the top of those columns anyway. That makes sense? But now, you can't, up to 7 here, those Roman numerals match what's here, but this 8, then 8, 9, 10, that all kind of starts to get off a little bit. That makes sense? And you can't depend on this 13 telling you that's not 13. But there's those Roman numerals are also on this periodic table. Okay? Then with acids, you have to first learn to name the ionic compounds, and then we'll change the ending of the names, the beginning of the names, to match the acid nomenclature system. Okay? So that nomenclature system includes, like hydrochloric acid. You first name that like an ionic compound, and you change it because it's easier to do it that way. Once you learn ionic, naming the acids actually becomes pretty easy. But we got to also, in this ionic section, learn to name polyatomic ions. So if you'll get out your periodic table, your references. I want to show you a reference here. You won't have to memorize or learn a naming system for the polyatomic ions because they're right here on this list, and you always have this list. You can have this list on your homework. You can have this list for your tests, classwork. You're supposed to have this list with you all the time. Okay? So if you look in here, you'll find polyatomic ions. So if you're trying to, please don't pack up just yet, okay? Give me your attention. All right, I'm still teaching, okay? If you see this formula here, you can figure out what the charge is. Then you just call it by this name. If you see this name right here, you know that's the formula right there. Okay? So that's what's on this chart for you. This makes it easy for you to figure things out. All right? In an honors class, you got to memorize a good number of these. Okay? You don't have this list in an honors class, but here I'm giving you the list for you to use as a reference. That makes sense? Okay. All right. So that's what we're going to start on after the test. Let's see. So A group takes the test on Monday. B group takes the test on Tuesday. So please stop just a minute and listen. On Tuesday, you will have a recorded lesson, okay, like before, like we're doing in the hybrid lessons in the beginning of the year, that you will do at home, okay? Because I can't teach you virtually while I'm also giving a test. That makes sense? Okay.
So we ain't gonna be in school?
Huh? We'll be back to the hybrid schedule for Monday, Tuesday, Wednesday, Thursday next week, and then we'll be back all together again on Friday.
Can you move that?
Move it where?
Right there, this is the front paper. Right.
Oh, you want to see this?
Yeah.
Okay, yeah. All right, so now you can pack up, guys. I'll look and see if I have, y'all ever used Quizlet before? No? I have some Quizlets for some things, and I may have a Quizlet for memorizing this numbering system stuff, okay?